January 17, 1942. Akron, Ohio. The sky hung low and gray over the industrial belt, pressing down on factory rooftops like a wool blanket soaked in sleet. Inside the Champion Spark Plug Company's plant number 3, the air tasted of graphite dust and burnt oil. Men in canvas coveralls stood shoulder to shoulder along assembly lines that had, until 3 weeks prior, produced plugs for Packards and Pontiacs. Now those same hands held calipers and micrometers, measuring tolerances down to the 10,000th of an inch. The fluorescent lights buzzed overhead, casting everything in a sterile white glow that made the workers' faces look gaunt, hungry. A supervisor named Harold Metz stood at the end of line 7, holding a spark plug in his palm, like a priest holding communion. It was smaller than the civilian models, lighter, and its ceramic insulator gleamed with a strange milky translucence. He turned it over slowly, studying the threads, the copper core, the way the glaze caught the light. Somewhere in the back of the plant, a furnace door clanged shut. The sound echoed through the high ceilings. Metal on metal, sharp and final. Metz knew what that sound meant. They were firing the first batch of high-altitude insulators. If they cracked, the entire contract would collapse. If they held, American bombers would fly higher than any aircraft in history. He slipped the plug into his breast pocket and walked toward the kilns. This was not a story about spark plugs. It was a story about porcelain and pressure, about the invisible war fought in temperatures exceeding 2,000 degrees Fahrenheit, where victory was measured not in miles gained or ships sunk, but in the resilience of a ceramic insulator no larger than a man's thumb. It was a war that began not on December 7th, but months earlier, in the cold arithmetic of aeronautical engineering, when American military planners realized that the bombers being designed to strike Tokyo and Berlin would have to operate at altitudes where the air was so thin, so cold, so electrically hostile that every component, every rivet, every seal, every plug would be tested beyond the limits of known materials science. And in that frozen crucible of thin atmosphere and sub-zero wind, the spark plug, that most humble and overlooked device, became the single point of failure that could doom an entire mission, an entire crew, an entire strategy of aerial dominance. Without it, engines seized. Without it, wings fell silent. Without it, the bombers that carried the hopes of a democratic civilization into the stratosphere became nothing more than 10-ton coffins tumbling back to Earth. The German Luftwaffe had learned this lesson early. In the spring of 1940, during the invasion of Norway, Messerschmitt Bf-109 fighters had climbed to intercept British reconnaissance planes flying above 25,000 feet. The German pilots, among the finest in Europe, found their engines sputtering, misfiring, losing power as they clawed for altitude. The problem was not fuel or oxygen or pilot skill. It was ignition. At high altitude, where atmospheric pressure drops to a third of sea level, the electrical environment inside a combustion chamber changes radically. The air is thinner. The voltage required to generate a spark increases, and the insulator that separates the electrode from the engine block must withstand not only heat, but also something called corona discharge, a halo of ionized gas that leaks voltage, fouls the plug, and kills the spark. German engineers working with Bosch had developed spark plugs with alumina ceramic insulators that could tolerate higher voltages, but even these failed above 30,000 feet. The Luftwaffe's ceiling was effectively capped. They could not chase the British Spitfires that flew reconnaissance missions at 35,000 feet, photographing German positions with impunity. They could not intercept the American bombers that were, even then, being designed to fly at altitudes the Germans thought physically impossible. The Reich's engineers knew they were fighting a materials problem disguised as a tactical one, but they did not have the materials to solve it. Across the Atlantic, American engineers knew this, too. In 1941, before Pearl Harbor, before the draft, before the factories had retooled, a small group of men from Wright Field in Dayton, Ohio, sat in a windowless conference room with representatives from Pratt & Whitney, General Electric, and Champion Spark Plug. They were designing the Boeing B-29 Superfortress, an aircraft that would fly faster, higher, and farther than any bomber ever built. Its pressurized cabin would allow crews to operate at 40,000 feet. Its 4 Wright R-3350 engines would each produce 2,200 horsepower, and each engine would require 18 spark plugs that could fire reliably in an environment where the temperature outside the fuselage dropped to 60 degrees, below zero. where the air pressure was 1/5 that of sea level, and where a single misfire could cause an engine to flame out, triggering a catastrophic loss of power that would send the aircraft into an unrecoverable dive. The men in that room understood that they were not simply building a better airplane. They were building a machine that demanded materials that did not yet exist, and the clock was ticking. Japan had already invaded China. Germany had already taken Paris. The window for American intervention was closing. If the superfortress could not fly, the war would be fought on terms dictated by the Axis. And that was a war America could not win. Harold Metz had not been in that room. He was a ceramics engineer, not a military planner. But he understood porcelain in a way that most men understood steel or wood. By touch, by instinct, by decades spent watching kilns fire and glazes bloom. He had joined Champion in 1927, straight out of Ohio State, and had spent 15 years perfecting the alumina insulators that kept spark plugs from shorting out in automobile engines. Alumina, a compound of aluminum oxide, was harder than glass, more heat-resistant than clay, and when fired correctly, nearly impervious to electrical breakdown. But it was also brittle. Drop it, and it shattered. Thermal shock it, heat it too quickly or cool it too fast, and it cracked like ice on a spring pond. Metz had spent years learning how to mix alumina powder with binders and plasticizers, how to press it into molds under thousands of pounds of pressure, how to fire it in kilns where the temperature climbed slowly, degree by degree, until the particles fused into a dense, glassy matrix. It was art as much as science, a craft passed down from potter to chemist to engineer. And now the military was asking him to make that insulator work at 50,000 feet, where the thermal and electrical stresses were 10 times what any automobile engine could produce. They were asking him to do it in 6 months, and they were asking him to do it without fail, because failure meant dead pilots and burning cities, and a war that might never be won. The first prototypes failed within seconds. Metz and his team fired the kilns in December 1941, just days after Pearl Harbor, when the entire plant was still reeling from the news. They pulled the insulators from the molds, installed them in test plugs, and mounted the plugs in a pressure chamber that simulated high-altitude conditions. The chamber was a steel cylinder the size of a water heater, lined with refrigeration coils that could drop the internal temperature to minus 60 degrees Fahrenheit, while a vacuum pump sucked the air out until the pressure matched that of 40,000 feet. Inside, a single spark plug fired again and again, a strobe of blue-white light in the darkness. The engineers watched through a porthole window, counting the sparks, waiting for the insulator to fail. It did not take long. At 32,000 feet, the insulator began to glow faintly, a dull orange line creeping up from the base. At 38,000 feet, the glow brightened, and tiny fissures appeared in the ceramic, hairline cracks that spread like veins through marble. At 41,000 feet, the insulator exploded. Not a loud explosion, but a soft pop, like a champagne cork, and the plug went dark. Metz pulled the plug from the chamber and held it under a magnifying lamp. The insulator had fractured cleanly down the center, split by thermal stress. The glaze had blistered. The electrode was scorched black. He set it on the workbench and stared at it for a long time, turning it over in his hands, searching for clues in the pattern of the cracks. Then he went back to the kilns. The problem was not the alumina itself, but the way it was fired. Traditional ceramics are fired in a single long cycle, brought slowly to peak temperature, held there for hours, then cooled slowly to prevent thermal shock. But this method produced insulators that were too porous, too electrically leaky for high-altitude use. The voltage would creep through the microscopic pores, creating pathways for corona discharge, and the plug would fail. What Metz needed was a denser ceramic, one with fewer pores, tighter grain structure, higher dielectric strength. To get that, he would have to fire the alumina hotter and longer, pushing the kiln to its limits. But if he fired it too hot, the ceramic would deform. If he fired it too long, the glaze would run and pool, ruining the threads. And if he cooled it too quickly, it would crack. He needed to find the exact temperature, the exact time, the exact cooling curve that would transform the alumina powder into a material strong enough to withstand the electrical and thermal hell of a high-altitude engine. It was a problem with a million wrong answers and only one right one, and he had to find it before spring. He worked through January and February, firing, batch after batch, adjusting the kiln temperature by 5 degrees, then 10, then 20. He experimented with different binder ratios, different particle sizes, different glazes. Some batches came out too brittle, some came out too soft, some came out perfect looking, gleaming and white and flawless, only to fail within minutes in the test chamber. Metz kept a notebook, a small leather-bound ledger where he recorded every variable: temperature, time, pressure, glaze composition, cooling rate, and every result: success, failure, catastrophic failure. The pages filled with numbers and sketches, cross-referenced and annotated, a map of trial and error. He slept in the plant some nights, curled up on a cot in the ceramics lab, the smell of kiln smoke in his hair and graphite dust under his fingernails. His wife stopped asking when he would come home. His son, 7 years old, stopped asking when Daddy would take him to the park. The war had swallowed him, not with bullets or barbed wire, but with the quiet, grinding pressure of a problem that refused to be solved. And still the insulators cracked. In Berlin, engineers at Bosch faced the same problem. They knew the Americans were building high-altitude bombers. They knew the Luftwaffe's spark plugs could not compete. But Bosch's kilns, some of the finest in Europe, were already running at capacity, producing plugs for tanks and submarines and trucks, and 500,000 other military applications. The German industrial base, stretched thin by years of war, could not afford to gamble months of production time on experimental ceramics that might not work. Instead, they focused on incremental improvements, slightly better glazes, slightly tighter tolerances, hoping to squeeze a few more 1,000 feet of altitude from their existing designs. It was a rational choice, a conservative choice, the choice of an empire that believed it was winning. But it was also a choice that ceded the high ground, literally and strategically, to the Americans. Because while Bosch played it safe, Harold Metz was burning through every rule in the ceramist's playbook, trying things that no sane engineer would try, firing kilns so hot the bricks glowed cherry red and the air shimmered with heat. He was not being reckless. He was being desperate, and desperation, when combined with resources and talent and time, has a way of producing miracles. The breakthrough came in March. Metz was experimenting with a 2-stage firing process, an idea he had borrowed from the porcelain industry. Instead of firing the insulator once, he fired it twice, at different temperatures, with a grinding step in between. The first firing, called a bisque fire, brought the alumina up to 1,800 degrees, just hot enough to fuse the particles into a fragile, porous body. Then he ground the surface smooth, removing imperfections and tightening the tolerances. Then he fired it again at 2,200 degrees, hot enough to fully vitrify the ceramic, sealing the pores and creating a dense, glassy structure. The second firing was risky. Many insulators cracked during the thermal shock of reheating, but the ones that survived were unlike anything Metz had ever made. They were harder, denser, more translucent, with a dielectric strength nearly double that of standard insulators. He installed one in a test plug and mounted it in the pressure chamber. The chamber cycled through its sequence, dropping the pressure, dropping the temperature, firing the plug again and again. 30,000 feet, 35,000, 40,000. The insulator glowed faintly, but it did not crack. 45,000 feet, 48,000. Still firing. Metz watched through the porthole, barely breathing, his hands pressed flat against the cold steel of the chamber. At 50,000 feet, the plug was still sparking, a steady blue pulse in the frozen darkness. He let it run for an hour, then 2, then shut down the test. When he pulled the plug from the chamber, the insulator was intact. No cracks, no blisters, no carbon tracking. He held it up to the light, turning it slowly, and for the first time in 4 months, he allowed himself to smile. Production began in April. Champion retooled 3 entire assembly lines, installing new presses, new kilns, new grinding stations. Workers who had spent their careers making plugs for Fords and Chevrolets now made plugs for B-29s and P-38s, measured to tolerances they had never imagined. The 2-stage firing process was slow, labor-intensive, expensive. Each insulator took nearly 2 days to produce, compared to 4 hours for a standard automotive plug. But the military did not care about cost. They cared about altitude. They cared about missions. They cared about bringing bombers back alive. By June, Champion was producing 5,000 high-altitude plugs per week. By August, 10,000. By the end of 1942, nearly 500,000. The plugs were shipped to Boeing plants in Renton and Wichita, where they were installed in the engines of B-29 superfortresses that would, within 2 years, fly higher than any bomber in history, higher than the Luftwaffe could intercept, higher than the Japanese air defenses could reach, and rain fire on the cities of the Axis with a precision and ferocity that would break the will of empires. The German pilots who faced those bombers did not know about Harold Metz. They did not know about Champion Spark plug, or 2-stage firing, or alumina ceramics. They knew only that the American bombers flew at altitudes where German fighters could not follow, where the air was too thin and the engines too weak and the spark plugs too fragile. They watched from below as contrails etched white lines across the sky, unreachable, untouchable, a symbol of technological superiority that no amount of courage or skill could overcome. Some German pilots tried to climb anyway, pushing their engines to the brink, feeling the sputtering, the misfires, the sickening loss of power as their plugs fouled and their engines died. They glided back down, powerless, humiliated, knowing that the Americans owned the sky, not because they were braver or more ruthless, but because they had solved problems the Germans had not even tried to solve. It was a bitter lesson, one that repeated itself in 1,000 small defeats, each one invisible, each one fatal. The Japanese had a different experience. In 1944, when the B-29s began flying out of the Mariana Islands to bomb the Japanese mainland, the Imperial Japanese Army Air Force scrambled every available fighter to intercept them. The Kawasaki Ki-61s and Nakajima Ki-84s, among the best fighters Japan had, climbed hard, engines screaming, pilots straining against the pressure of altitude, oxygen masks fogging, fingers numb on the controls. They reached 28,000 feet, then 30,000, then stalled, unable to climb higher, unable to reach the bombers cruising effortlessly at 35,000 feet, their right engines humming with the steady, reliable fire of champion ceramics. The Japanese pilots descended, defeated not by American guns, but by American engineering, by a supply chain that stretched from the aluminum mines of Arkansas to the kilns of Ohio to the assembly lines of Seattle, a chain of production so vast and so efficient that it could turn raw earth into strategic dominance in a matter of months. They returned to base and reported what they had seen, and their commanders listened with expressions of stone, knowing that the war was already lost, that no amount of samurai spirit or kamikaze fervor could bridge the gap between a nation that could make spark plugs fire at 50,000 feet and a nation that could not. But the spark plug was not just a technical achievement. It was a symbol, a physical manifestation of a philosophy that the Axis powers fundamentally misunderstood. To the Germans and Japanese, war was about will, about discipline, about sacrifice, about bending men to the demands of ideology. To the Americans, war was about production, about logistics, about solving problems with resources and ingenuity, and an almost reckless willingness to experiment. The spark plug was the distillation of that philosophy, a small, mass-produced object, invisible to the casual observer, but essential to the functioning of the entire machine. It was not heroic, it was not glorious, it was simply necessary, and that necessity, repeated 1,000,000 times across 1,000,000 components, from spark plugs to ball bearings to synthetic rubber to radar tubes, built an arsenal that the Axis could not match, could not even comprehend. Because while German engineers debated the theoretical limits of ceramic dielectrics, American engineers like Harold Metz simply went into the lab and solved the problem. While Japanese factories struggled to produce enough steel for ships and tanks, American factories produced enough alumina to make insulators for every bomber, every fighter, every transport plane in the Pacific. It was not magic. It was not genius. It was simply America, doing what America had always done best, turning raw materials into finished products with a speed and scale that defied imagination. By the end of the war, Champion Spark Plug had produced over 20 million high-altitude plugs. They were installed in B-29s that bombed Tokyo, in P-51 Mustangs that escorted bombers over Berlin, in C-47 transports that flew the hump over the Himalayas, in every aircraft that needed to fly high and fast and far. And in every one of those plugs was the ghost of Harold Metz's two-stage firing process, the invisible labor of thousands of factory workers who mixed alumina and pressed molds and tended kilns, the accumulated knowledge of chemists and ceramists and engineers who had spent decades perfecting a craft that no one outside the industry even knew existed. The plug became a metaphor for the American war effort, small, overlooked, essential, the product of a supply chain so deep and so resilient that it could absorb losses and adapt to challenges and keep producing day after day, month after month, until victory was not a question of courage or ideology, but a question of mathematics, of tonnage, of the sheer weight of material that a free society could bring to bear when it chose to fight. The German soldiers who surrendered in the spring of 1945 had expected to fight a war of tanks and artillery and infantry. They had trained for it, bled for it, died for it. But in the end, they were defeated by things they never saw, by spark plugs and ball bearings and aluminum alloys by the invisible components of a war machine that stretched from the mines of Minnesota to the assembly lines of Detroit to the airfields of England. They had expected to face warriors. Instead, they faced accountants and engineers and factory workers, men and women who waged war not with rifles, but with production schedules, who measured victory not in territory gained, but in units shipped. It was a kind of warfare the Germans had not anticipated, and by the time they understood it, it was too late. The factories of the Reich, bombed into rubble by the very bombers that flew on champion spark plugs, could no longer compete. The war was over, decided not on the battlefield, but in the kilns of Ohio, in the furnaces of Pittsburgh, in the assembly lines of a nation that had turned its entire industrial capacity toward a single purpose and would not be denied. After the war, Harold Metz returned to civilian production. The kilns that had fired insulators for B-29s now fired insulators for Buicks and Oldsmobiles. The two-stage process he had pioneered became standard across the industry, adopted by manufacturers around the world, a quiet revolution in ceramics engineering that no one outside the trade ever noticed. Metz himself never spoke much about the war years. He did not consider himself a hero. He was an engineer, a problem solver, a man who had been asked to make a thing work and had done so. But when he retired in 1963, the company gave him a small plaque, brass with black engraving, that read, "For service to the war effort, 1942, 1945. He hung it in his garage, next to a dusty shelf of old spark plugs, and sometimes, when he was out there tinkering with a lawnmower or a chainsaw, he would glance up at it and remember the months when every spark plug mattered, when the fate of entire missions hung on the integrity of a ceramic insulator no larger than a child's thumb. And he would smile, just a little, and go back to work, because that was what engineers did. They solved problems. They made things work, and they did not need parades or monuments to know that they had done something important. There is a spark plug on display at the National Air and Space Museum in Washington, D.C. It sits in a glass case, next to a cutaway model of a Wright R-3350 engine, the kind that powered the B-29 Superfortress. The label beneath it reads, Champion High Altitude Spark Plug, circa 1943. This plug enabled American bombers to fly at altitudes beyond the reach of Axis interceptors, contributing to air superiority in both the European and Pacific theaters. Visitors walk past it every day, barely glancing at it, their eyes drawn instead to the Mustang hanging from the ceiling, or the B-17 fuselage in the next gallery. And that is as it should be, because the spark plug was never meant to be seen. It was meant to work quietly and reliably, firing 1,000,000 times over the course of a mission, turning fuel and air into thrust, turning strategy into reality, turning the ambitions of free men into the hard, cold facts of physics. It was meant to be forgotten, replaced, discarded, a consumable part in a war that consumed everything. But it was also meant to be remembered, not for itself, but for what it represented. The idea that freedom is built not on grand gestures, but on 10,000 small acts of competence. That democracy survives not because it is noble, but because it is efficient. And that the greatest victories are often won, not by the men who pull triggers, but by the men who make sure the triggers work. In the end, the spark plug asks us to see war differently, to look past the drama of battle and into the quieter, harder truth of production. It asks us to honor not only the pilots who flew the bombers, but the ceramists who fired the kilns, not only the generals who planned the campaigns, but the engineers who solved the problems, not only the soldiers who died for freedom, but the factory workers who made freedom possible. It asks us to remember that the machinery of democracy is built from 1,000,000 small parts, each one essential, each one the product of knowledge and skill and labor, and that the true measure of a nation is not the courage of its warriors, but the competence of its craftsmen. America had no spark plugs in 1942, but it had Harold Metz, and it had Champion. And it had 1,000 factories full of men and women who understood that winning a war was not about fighting harder, but about working smarter, about turning problems into solutions, and solutions into products, and products into power. And in the frozen darkness of 50,000 feet, where the air was too thin to breathe and the cold could kill in seconds, those spark plugs fired again and again, a tiny blue light in the void, proving that even in the depths of war, even in the face of tyranny, even when everything seemed lost, American ingenuity could still find a way to make the engine run.